Okay. Yeah. Welcome, everyone. I'm Roel van Beeumen from Lawrence Berkeley National Lab and from KU Leuven in Belgium. And today I'm going to talk about efficient LCU block encodings through Dicke-state preparation. And this is joint work between Filippo, Martina, and Luigi. And I have the pleasure to present these really great results. And the people who did the hard work are Filippo and Martina, who interned with me last year at Lawrence Berkeley National Lab. So we have two preprints. The first part will be about the first one. It's the block encodings through Dicke-state preparation. And then we have some recent results where we leverage this to also go to controlled block encodings, which enable efficient Hadamard tests, as well as polynomial transformations. And then all software and circuit implementations are available on GitHub. Okay, here is an outline of my talk. First part, we'll start with introducing block encodings. What are the main bottlenecks there? Then in the second part, I will introduce the Fast One-Qubit-Controlled Select LCU. We abbreviated it as FOQCS LCU, and that's why we use the FOQCS symbol, just easier to talk about. And then in the second part, I will talk about the polynomial transformations we will be able to carry out and give some practical, explicit quantum circuits. Okay, let's start with matrices. So I'm an applied mathematician by training, especially from the field of numerical linear algebra, and we love matrices. So today I'm going to focus on square matrices of exponential size. And matrices have applications almost everywhere. And for an applied mathematician, what is interesting, we can compute eigenvalues and eigenvectors of it. We can solve linear systems with it. We can compute matrix functions or matrix functions applied to a right-hand side B. And all these type of matrices, they have particular properties. They can be small, they can be large, they can be dense, they can be sparse, diagonal, symmetric, Hermitian, name it. But in general, these matrices are not unitary. And of course, quantum computers are great to work with unitaries, a little bit less great when we have non-unitary matrices. So here is the general definition of block encodings of matrices. Basically, what we do is we embed a scaled version of the matrix A into a larger unitary. We can write it in that notation. But what is the problem? Building blocks, block encodings are often crucial building blocks in many quantum algorithms. Think about the quantum singular value transformation, Grover search, and so on. However, they are often treated as a black box subroutine. So we have algorithms which are optimal in terms of query complexity to a block encoding. But if we cannot implement that block encoding efficiently, yeah, all the speed up can be annihilated. And so rarely these block encodings are constructed explicitly in practice. And that's actually what my talk will be about. How can we construct for certain classes of matrices or Hamiltonians explicit and practical short-depth quantum circuit? So for that, I'm going to start with a simple matrix example. And assume we have an n by n matrix A. Then we can always write an n+1 qubit unitary. So we double the size, and we don't care what the star elements in the matrix are. So these are n by n matrices, but they just make the overall U of A unitary. So if we then consider a corresponding n qubit quantum state B, and we also extend that quantum state to an n+1 quantum state by just adding a 0 ket in front, so we have a block B and a 0 block, then we know that if we apply this block encoding U of A to this extended B, that we obtain a 0 state and times AB plus some orthogonal state we don't care about, but in matrix notation we have AB in the top block and some other stuff in the block below. Now, if we go to the quantum circuit, we can say we have U of A is a large unitary. We have an ancilla qubit 0 and an ancilla qubit B. So imagine this is just a 2 by 2 matrix. So it's A is a 2 by 2. So U of A will be a 4 by 4, so 2 qubits. And if we measure the top qubit in 0 and do some post-selection, then the second qubit will be in the state A times B, so the matrix vector product A times B, and then, of course, normalize. Now, the success probability is equal to the norm of AB squared, and is independent of these arbitrary elements in the unitary U of A. Now, we have a unitary requirement on the matrix U of A, so we have to make sure that the norm of A, which we input, is equal or lower than 1. If that's not the case, we can just do some normalization. Yeah.
Just conceptually, how do we know that that block encoding always exists? Because as a counterexample, I might present a linear map. Because A is a linear, the matrix representation of a linear map. And suppose the kernel of that map is entire, that whole space. I now have to embed that in a larger space such that that map together is invertible. I mean, that's the minimum requirement for unitary.
Yeah.
So how do I invert something whose the fibers of that are the entire space?
Yeah. Therefore, we use the degrees of freedom in these arbitrary elements. And on the matrix side, you can prove that that always exists. However, on the quantum side, it doesn't mean that an efficient circuit exists for it. So
I'm just trying to think how, even if you just think that A, it goes to it's a constant.
Even if A is, for example, 0, one element, zero map, then you can fill up these elements to make it unitary. And for example, is the X gate is then a unitary, where your A is 0.
So 0 on the other side would go where? In the domain, in the codomain. Is it sending everything to 0?
Yeah.
I need to invert that.
No. It's only sending the top part to 0. And not the bottom part.
Yeah.
So you need to expand your space.
Sure.
In order to,
I'm just wondering, even in that expansion, I don't know where that goes, but maybe I'll just think about it.
It's possible. So you can prove it. It's always, if you add an extra qubit, it's always possible to find the unitary. Now, the biggest problem is that in practice, there is no guarantee that if you add the qubit, that you will find a polylogarithmic circuit. And therefore, what we're going to use is we are not going to add 1 qubit, but we are going to add a ancilla qubits. And that will allow us to have more degrees of freedom, and we will exploit that. And in particular, why we are doing it, if we look at the current quantum hardware, we see that the number of qubits are scaling much more rapidly than the circuit depth. So what's often the bottleneck is how many gates we can apply, basically the CNOT depth, before we just start measuring random noise. And we will use that property, so we will use a bit more ancilla qubits in order to come up with much shorter quantum circuits. So for block encodings, a commonly used technique is the linear combination of unitaries, or abbreviated as LCU. And LCU goes as follows. Assume we have a matrix or a Hamiltonian H written as a linear combination of unitaries UM, and alpha M here are the coefficients. So then this is the standard LCU textbook implementation, where we have some state preparation oracles, PR and PL, which encode the coefficients alpha M. And then we have what we call in the middle the select oracle, which based on these ancilla qubits, where we have log of capital M, they select which unitary to apply. Now the problem is, with this textbook example, is that this is not practical. And mainly because of these multi-controlled unitaries, UM. Because if we want to implement these multi-controlled unitaries, we have to decompose it in native 1 and 2 qubit gates, and we get really, really long quantum circuits. Now note that if we do some post-selection on all the ancilla qubits, we get the quantity h times the vector psi we want to compute. So a little bit more in detail, we have three oracles which comprise the LCU circuit. The first is the state preparation oracle PR, which maps these coefficients, linear coefficients, into a certain superposition. Then we have the select oracle, which selects which unitary we have to apply. And then we have the PL oracle, and that's basically just doing the back transformation. Note that it's almost the same, except we have a complex conjugate there. Okay, this is already a bit the conclusion of the FOQCS LCU circuit. So instead of having this circuit, the standard LCU, we cannot implement in practice, we came up with the following one. Note that we now use not log capital N ancilla qubits, but we use 2n ancilla qubits. And by using these 2n ancilla qubits, we are able to get rid of all these multi-controlled gates in the select oracle. And basically, we have just some layers of CNOTs and some layers of CZ gates. And all these CNOTs, since they act on different qubits, can be executed in parallel, as well as all these CZ gates. So the select oracle here, in this case, circuit depth 2. Trivial. Of course, we still have the PR and the PL. And for PR and PL, for certain algorithms, for certain Hamiltonians, we're able to come up with also linear depth or quadratic depth circuits by exploiting Dicke-states, and that I will explain in the second part of the talk.
Yes. N, little n related to M? Or...
there is actually no relation between that, but the maximum number of terms of capital M is 2 to the 2n, so that corresponds to all the ones we have here. Yeah. So worst case for the standard LCU, you would also have 2n extra ancilla qubits.
Mm-hmm.
So instead of having n qubits for the state, we just need 3n in total. So it's still linear. And the prefactor is 3. So since the second part of the talk is rather technical, I just want to briefly introduce some 3 key results, just to keep the high-level overview of the talk. So the first thing is that we have practical and explicit FOQCS LCU block encodings for spin Hamiltonians, where we have these select oracles, just a parallel layer of CNOTs and a parallel layer of CZs, and then PR and PL we will be able to efficiently implement through Dicke-state preparation. The second contribution is that we can control these FOQCS LCU block encodings trivially. Actually, we can write it as follows, but of course, we still have a control on the full PR, but we will show that for these particular spin models, where we use Dicke-state preparation, we can control these PR and PL with just one extra CNOT. So controlling a FOQCS LCU is 2 extra CNOTs, trivially. And then the third key contribution is that we can leverage this FOQCS LCU block encoding framework to apply polynomial transformations of the matrix H. And of course, we use a bunch more ancilla qubits. We will use now dn instead of 2n. I think no, it's 2 times dn, where we have now some layers of the select oracle, but then we have this controlled PR, which we can also do with just one extra CNOT. And note that all these PRs can be just performed in parallel because they are acting on different qubits, the same on PL. But more about that in the third part of the talk. Yes?
You're introducing a lot of ancillas, which you're measuring to be zero, and the success probability you'll probably talk about later could start getting very, very small in this case.
That's indeed a good question. Now, the success probability, what we know is, where is it here? Measuring zero is independent of how many ancilla qubits we use. So,
okay, so even though it's distributed, so there's a much larger space, the success probability hasn't gone down.
No, it's the same success probability which you have with the standard LCU. It can be that it's pretty low, but then it's not that we make it worse. Yeah. Okay, so let's start now with the Fast One-Qubit-Controlled Select LCU, or FOQCS LCU. And I'm going to start simple again, a 2x2 matrix. So just introducing the Pauli matrices. I ordered them in this way. So we have z and x, and especially y we can write as minus the imaginary z times x. And what we do is, suppose we have a complex matrix H, 2x2. Then we can write this H as a linear combination of four terms: the identity, a z term, an x term, and a y term. And then if we substitute the y by minus I zx, then we notice we only have z and x. And then we can make use of the check matrix formalism, where basically we have an index I and an index j, and I stands for x and j for z, where we see, like, if we apply an x or a y, I is 1, and otherwise it's 0, and it's the reverse for j. So what we now can use this I and j for is basically we write a z, or a z to the power j, and x to the power I. And based on the values here, we can select which term we have. If both I and j are 0, then we end up with the identity matrix.
What happens to your minus I with that?
The minus I is just a scale. Of course, we have to change these parameters.
Okay, so that gets absorbed into alpha 1.
Yes, yeah. So what we can do is we can write it now as follows. Since we have two ancilla qubits, where the top one corresponds to I, which will select the x, and the second one corresponds to the z. And then based on the x, we will have the CNOT and then a CZ. So this PR and PL, basically what they do is they prepare this superposition with the coefficients alpha 0, 0, alpha 0, 1, and so on. And as you can see, we absorb the minus I into this coefficient. So important to note here is we have only one CNOT and one CZ gate. No multi-controlled gates, because, for example, if you would implement that linear combination with the standard LCU, we would have a PR and a PL, and also we would require two ancilla qubits, because you have four terms, so log 2 of 4 is 2. So, but then you would have a multi-control on so you would have four multi-controls for selecting I, Z, X, and Y. Now, we can generalize this to an n-qubit matrix. So we have a 2 to the n times 2 to the n matrix, and we assume that it's decomposed in polystrings. So we can write it as follows. We make the assumption that the one norm of A is just equal to 1, otherwise we do a rescaling. What we're now going to do is we're going to map each of these polyterms to a binary pair. And that's what I said before. We will have now like z to a power j and x to a power y. And depending on the binary value, we select whether we have an I, an x, a y, or a z term. And then what we can do is we can combine all these binary representations into a n-qubit index, both I for x and j for y. And then we obtain what we call the check matrix decomposition of the matrix H. So where we now don't have the Pauli terms, but we only have z to the power j times x to the power I, where I is an integer, but we use the binary representation. And then we have some alpha ij tilde parameters, which have exactly the same sparsity pattern than the original ones. Also, the magnitude doesn't change. It's only if certain term, like if both I and j are equal, then we apply a scalar multiplication minus I. So how do we now represent that in a quantum circuit? What we will have is we will have two ancilla registers where the top n qubits represent to the x register I, this part here. And then the second one is what we call the z register for the indices j. And we see that the I indices, they are the selection for the CNOT gates and the j for the CZ operations. So, of course, we need the state preparation pair PR and PL, which is here the general expression. And of course, we still have to come to how do we efficiently decompose these. But for now, we got rid of all the multi-controlled gates in the select of the LCU. And we only have NC-NOTs and NCZ gates, but all these C-NOTs and CZs can be performed in parallel. So if we look at only the select oracle, the circuit depth there is 2 C-NOTs or 2 CZs, whatever, but 2 entangling 2-qubit gates. Okay, so now we're going to focus on how can we make this PR and PL efficient. And for that, let's talk about Dicke-states. So, do an intermezzo. I don't know how familiar people are in the audience with the Dicke-state, but I'm going to start with the simplest one, and that's what people call the balanced Dicke-state with just one excitation. And it's an equal superposition of the 0001 state plus 0010, and so on. And if we use some binary representations of these states, we can write it as a summation of the states 2 to the L, where we let L run from 0 to n minus 1. And we normalize it, of course. And for this, there exist efficient quantum circuits to prepare. So we can say, we can prepare a balanced Dicke-state with just one excitation, starting from a 0 input state, and then run this circuit. Of course, these angles and so on, we can all compute. And what we have is, this is the circuit that basically the block of a controlled RY followed by a CNOT can be decomposed together in just 2 CNOTs. So then if we count, we have 2 to the n minus 1 CNOT depth for a Dicke-state. Can make it a little bit more complicated, also an unbalanced Dicke-state. So now we just have a factor alpha L in front of the terms. And we can also come up with the efficient linear depth circuit. We have exactly the same as for the balanced one, and then we add some phase gates to compensate. But okay, phase gates, just 1-qubit gates, we assume they don't contribute to our 2-qubit depth. So the same CNOT cost as for building or preparing a balanced Dicke-state.
So these alphas are arbitrary normalized.
Yes. Yes. Yeah.
They just go into the phase.
They go into the phase, and also in the angles of the RY gates.
Okay, right.
Yeah.
Yeah. Right. Yes. So there's RY.
And especially these are if these alpha i's are complex. If they are real, we don't need the phase gates. But since we push, like we have the minus I into the Y terms, we need sometimes the phase gates. But yeah, and then it's just, and we have a simple formula, it's in the paper, how to compute these angles. So that we can do all classically, of course. Now, we will also need more complicated Dicke-states and Dicke-states with two excitations plus some nearest neighbor constraint. So we now have a Dicke-state where we don't have 2L, but also 2L minus 1. So we will have a superposition of states 0, 0, 0, 1, 1, plus 0, 0, 0, 1, 1, 0, and so on. We can also have k nearest neighbor constraints, and they have very similar circuits. So the blue block is basically, or all the blue blocks are preparations of one qubit, one excitation Dicke-states, and then we add one layer of CNOT. And that means still linear depth in the number of qubits. Now, why are we doing that? I'm gonna try to explain it for the Ising model. It's one of the simplest models to explain, and also the circuits will still fit on the slide, but I will give more complicated circuits and models later on. So let's start with a definition of the 1D Ising Hamiltonian with open boundary conditions. So we have some z terms and we have some x terms, all nearest neighbor. And what we're gonna do is, in order to exploit the Dicke-state preparation, is we're gonna, of course, map all these coefficients to a coefficient state pair. And what we can see is, for example, for the L term with the z component, we have some identities, and we have J, Z, and also some Kronecker identities. What we can do is we can rewrite it as a zero state on n qubits, and then a state like this. And we can write it as follows, with where we have 0 and then 2 to the L. And this 2 to the L, if we make a summation over it, we get some Dicke-states. And that's where the key lies. So for the whole, like also for the x terms, we get now 2 to the L plus 2 to the L plus 1. If we go back to the Dicke-states, that's exactly what we have here. So what we will do is, after this mapping, we will be able to leverage the Dicke-state preparation, both for one excitation as well as two excitations plus nearest neighbor. I know these are complicated formulas, but the top one is just the definition. Then what we do is we fill the terms in, and of course here we have on the top row we have 2 to the 2n terms, but only a linear number of them are non-zero. If we exploit that, then we can come up with a superposition of Dicke-states with one excitation and a Dicke-state with two excitations and nearest neighbor connectivity. Now, this is the overall circuit for, I think 6. So n equals 6. It consists of 4 blocks, 1, 2, 3, 4. And wait, in the next slide, I'm gonna explain all of these blocks separately. It's a dense slide, but I'll walk you through it. So we have, this is the Hamiltonian. The Ising Hamiltonian, we have z terms, x terms. So we know that the state preparation oracle can be represented as a superposition of the Dicke-states and nearest neighbor Dicke-states. Here I'm only working on PR. We know for n qubit state we would have 2n ancilla qubits, so this just represents the ancilla qubits, where the top 6 are for the X register and the bottom 6 are for the Z register. So what we first do is we're gonna look at the terms J, G, and J. And what we do is we have, of course, we need some X states, and then the RY the angle will depend on J and G. And what we do is, of course, we start at the beginning with all 0, and then we split out in a 0 and 1 term, and you can see it as we split out in an x1 and a 0 term. What we then gonna do is we need the Dicke-1 for the z terms. So that's the preparation of the Dicke-state of the first term, and it corresponds to this part. So that's the Dicke-state notation. This is the notation in the formula. What we're then going to do is on the top part, we are now going to work on the x. But what we do is we first do the Dicke-state with one excitation, but then we still need to add another one, and then we add this extra layer to create the double Dicke-state. So this is a bit an overview of how we do that, and we can do that for many other models where we have certain terms here. The goal is here to come up with short depth circuits, and if we count the number of CNOTs, taking into account that these blocks we can simplify, we only have a depth, CNOT depth of 2n. So for the whole PR oracle, independent. So that means we only need 2n CNOTs. We have a little bit more. Of course, if we use 2n ancilla qubits, then we can implement the PR oracle with only 2n CNOT depth. Yeah.
Total number of CNOTs then effectively scaling as the number of non-zero terms in your Hamiltonian in this case. Every new term you've just got to couple to another one.
Yes.
Probably rotation. So.
Yeah. So if we look at the formula, we have a linear number of input parameters. We also get a circuit depth, which is linear. And I'll show you later. I think in 2 slides, I have a graph to compare with the standard LCU. So this is the overall, so the complete FOQCS LCU circuit for n qubits, where this part is PR, this is the select, this is PL, where we have the X register, the Z register, and then the actual state. And then if we sum up, of course, we have 2n for PR, 2n for PL, and then this counts in depth just as 2 CNOTs. So we only need 4n plus 2 CNOT depth for this circuit. And actually, what you can see is we have all this long range interaction. If we do it in 1 qubit, I'll explain in the next part that on a 2D grid, this is all nearest neighbor. So we can also implement that all with nearest neighbor interactions. So let's go to some more complicated and more interesting problems. I'm going to start with the 1D Heisenberg Hamiltonian with open boundary conditions. And again, we can do the same here, map each term to a coefficient state pair. Then we get some Dicke-states with 1 excitation, and then Dicke-states with 2 citations and nearest neighbor constraints. And here are some, there's a comparison for CNOT count for this model, where basically we have the FOQCS LCU, and we see it scales linearly with the number of sites or number of qubits of your model, whereas the red curve is scaling superlinearly. What we did here is we, of course, used the standard formulation, put it in Qiskit, then even used Biscuit, got another 10%, but already for 16, so your state of 16 qubits, you have more than an order of magnitude difference. Then we compared it to Fable, so it's a fast approximate block encoding technique we developed a couple of years ago, of which we know it scales exponentially. And we can do some truncation, and based on the truncation parameter epsilon, it's a bit competitive, but yeah. Now the thing is, why is it better here? Is because it's all approximate. We didn't took into account that if we have small angles, we can truncate it and so on. But of course, that's for really, really tiny models. Now, if you look at the scale, it's about 100. Here it's about, I think, 700-800. CNOT depth, or CNOT, this is total CNOT count. CNOT depth is even much lower. That means that brings us much closer to actually execute that on actual hardware. So rather than here, we are talking about more than 10,000 CNOTs. That's not so near term. Compared to here, we are below 1,000. And that's hopefully, we're actually working on it to run it on actual hardware. Now, as I said before, we have these 1D circuits, but if we map it to a 2D qubit layout, everything becomes nearest neighbor. And I'm gonna try to explain that for the XXZ model, not the XYZ model, because then it doesn't fit on the slide anymore. So we can, of course, do it in a very similar way. So we have some XX, ZZ, and YY terms. Again, we do the same mapping. And here is the overall circuit for the PR oracle. So again, we create some nearest neighbor stuff. So this is one Dicke-state, another Dicke-state. We have the CNOTs to make that nearest neighbor. And then we need what we call a double Dicke-state, because we have both the X and the Z registers, which are activated. And then we just add some controlled RY. Note the circuit depth is still 2n plus 4. Now, I think before it was 2n, now we have a constant factor 4. These 4 extra CNOTs are not going to matter that much. So let's have a look. What I've now done is here plot the layout of a 2D qubit connectivity, where the top one is for the ancilla qubits, or for the X register. This is the Z register, and here lives the quantum state, sorry, which is, and this will be an example for 6 qubits. So a 6-qubit state. That means we need 11 qubits, 12 qubits, ancilla qubits. So the first part is basically taking into account some of the coefficients. Here we do all these things. That's not that interesting, but this part becomes more interesting. We can apply these controlled RYs together, the CNOTs in parallel, and then the moment we apply these controlled RYs, we can already apply this one, because nothing is happening there, and you see it's all nearest neighbor. We can continue where we do all these, this CNOT, this CNOT, this CNOT, and this CNOT all together, and so on. And we can continue. So can be done very efficiently. We have PR, which is done. Then what we're going to do is to apply this select. It's just a layer of CNOTs and a layer of CZs. What we do is we have to first swap the state with the Z register. We apply X, and then we can apply the CZs all in parallel, and all nearest neighbor gates, or gates act 2-qubit gates acting on nearest neighboring qubits in a 2D layout. So that means even if you consider an all-to-all connectivity going to a 2D layout, we have the similar, like exactly the same circuit depth. And then we have to do some swapping back, of course. And that brings us to a total depth for the whole circuit of 4n plus 10. So it's all linear depth. We can do it for other spin models. Here is the XYZ model, the 1D Heisenberg model. And then we've also generalized it for spin glass Hamiltonians, where now we don't have constant terms, but these terms can vary. What we have basically, since we have a double sum here, we have, instead of a linear, here we have a quadratic number of coefficients, and basically a quadratic number of classical input. And then if we look at the total CNOT count, then we see that the FOQCS LCU has a quadratic complexity, whereas the standard LCU has, almost 2 orders of magnitude more CNOTs we have to apply. Okay, we need a little bit more ancilla qubits here. Instead of 2n, we used 5n. But okay, we assume we have that available.
So that number of ancillas doesn't scale. Where does the pi come as opposed to that?
Actually, that was in order to, since we have a quadratic number of terms here, either we used some unity encoding. So for the coefficients to avoid multi-controlled gates. Yeah, but Filippo has a better implementation already for this. But I think we can also bring it down to only 2n. So yeah, but this is what we have in the paper now.
In that spin glass, it's no longer nicely local. Because of the explicit,
you have more gates, but also it's a more complicated model. But in the end, your CNOT, this is total CNOT count. It's quadratic. The CNOT depth, the prefactor will be much lower, but it's still quadratic. But that's what we expect if we have a quadratic number of classical input parameters. Then having a quadratic CNOT depth is what we have to live with, I think. Of course, here we use this Dicke-state preparation where we don't do mid-circuit measurement. And there are some, for the simplest Dicke-states, you can do it even in constant depth. But then you have to allow for mid-circuit measurements. We know for certain models it's for sure possible. We're still seeing and trying to see whether we can generalize it for the more complicated ones. So potentially we can even get some of these terms even much lower. Okay, that was the most theoretical part. So now let's go to some applications of this FOQCS LCU block encodings. And before we go to the polynomial, if we want to make a matrix polynomial, what we have to do is we have to do powers of h. And let's start with h squared. So it's basically 1h Hamiltonian written in the check matrix formalism times another one. Then we can work it out as just not having a z and x, but now 2 times. And we can implement it as follows as a circuit. Now, since we have h squared, we don't have 2n, but we have 4n ancilla qubits. But the nice thing is, we can do these PRs. We can show that we can just have exactly the same PR for this one, but just repeat it. And so that's keeping the circuit depth exactly the same. So we have now I, J, P, Q, and P here. We have now, this can be done in parallel, so we would have not 2n depth, but 4n. And we can generalize this further. If we want the cubic term, we just add 2n extra ancilla qubits plus 2n in the circuit depth. So with more qubits, but almost exactly the same or very similar number of CNOT gates or CNOT depth, because the number of CNOTs will increase, but they are all in parallel, and we assume that's not the biggest issue. Now, how we go to polynomials in H. So this is the mathematical formulation we want to do is we want to have a polynomial where we have some coefficients a0, a1, and so on. And then we have these polynomials I, h squared until hd. What we do is we add an extra LCU on top of that. And what we do is we have an LCU here, a poly. This is for the coefficients a1, a0, a1, and so on, where we use a unary encoding. So that means actually that if we would have d equals to 3, that's what the circuit is plotted for here, we use 3 extra ancilla qubits to avoid multi-controlled gates of the PL. So this is exactly the same as h to the third in the middle without these 3. Now we have these controls, and I will show that we can, for all the FOQCS LCU circuits, I've shown in the talk and also in the paper that these controlled PR and controlled PL will require just one extra CNOT. And why is that? That's because we start here with the 0 state, and here for PL dagger, we measure in the 0 state. So what we can prove is if we have a PR, then here I think this is the example for XYZ model, it doesn't matter. We can just pull out one X gate and then define a PR tilde that if we control that PR and start with the 0 state, then we can write it as the controlled X, so one X, one CNOT, and then the PR tilde not controlled. And the same we can do with the controlled PL. If we measure all the qubits in 0, we can just split off that extra CNOT, extra X gate, and then control that X gate to have one CNOT. So this shows the circuit for controlling a full FOQCS LCU circuit. So it's not a polynomial. So basically we have now one CNOT here, one CNOT here, the PR and PL tilde, and then the select oracle in the middle. So that means controlling the FOQCS LCU circuit, we require just 1, 2 extra CNOTs. So that opens the door, for example, the Hadamard test, to do some efficient Hadamard test. I'll come back to that in a few seconds. Now, the polynomial transformations. So here is the circuit for again, and let's have a look at mainly the circuit depth. What it will be is we have the depth of PR, where we know for Heisenberg models, 1D models, it's linear. For example, for the spin glass models, it's quadratic. Then, of course, we have the depth of PL. And then we have here, that's just 6D together with these CNOTs and the Pauli. This is basically just, I think, also 1 or 2D. But important to notice is we have, let's say, the depth of PR and PL are independent of the degree, and they are, let's say, the number of qubits. And then we have a factor D. If we look at the quantum singular value transformation, there they are all block encodings are behind each other. There you would have your n times d. Of course, you require less ancilla qubits, but your circuit is going to be much, much longer. So here we use the freedom of block encodings to, use more ancilla qubits and trade in some circuit depth.
In some sense, is this the most compact you can get? Because at some point you've got to encode your Hamiltonian three times to get h cubed. Effectively, you need to apply it 3 times, you can't clone that. And so this only encodes it 3 times in the PRs. So you can't really reduce that, as far as I can tell.
I don't want to claim it that it's the most compact one, but as far as we know, it's one of, it's the most compact until now, if we have the freedom to add more ancilla qubits. But so far, we haven't been able to prove that. That would be interesting too. Okay, so a few last examples. First, the Hadamard test. So Hadamard test is a standard quantum circuit for estimating the expectation value. Here, so what we do is we add one extra ancilla qubit, apply a Hadamard gate to a control U, and then apply the Hadamard gate again. And then we get the real part out of it. We can also get the imaginary part if we measure, I think, in the Y basis. But that's not so important now. In case that H is a non-unitary operator, what we can do is we can embed that in a block encoding. If we use then our FOQCS LCU block encoding, of which we know that controlling just adds 2 extra CNOTs, we add 2 n circuits, 2 n ancilla qubits for the block encoding. If we measure them all in 0 and do some post selection, then we get out the real part of the expectation value of H by using that block encoding. Now, if we look at the CNOT counts and the CNOT depth of this Hadamard test, which appears in a lot of applications, then we can see here the colors correspond to different models. So we have the XY model, which is Heisenberg, of course, XYZ model, most expensive one, the XXZ, and then Ising. Nice thing to notice is that if we have an all-to-all versus a square grid qubit connectivity, there is just a vertical shift, and that's because we have to do a few extra swaps. But it's not that much. It's like, yeah, probably 6 or 8 extra CNOTs, because note that is all in linear scale. But just to give an idea, to do a Hadamard test for an XYZ model, you are still below 200 CNOTs for 20 sites. Of course, the number of qubits will be, if we say for 20, that would be 20, 40, 60, 61. That's within reach of what we have today. So that brings us definitely much closer to actual hardware runs, which you're trying to perform at the moment. Then as a last example, gonna talk. Yeah, thanks. Yes, sure.
Can we go back?
Yeah.
Did you try other geometries and see about that spherical?
We didn't. No. Do you have a certain geometry in mind, or?
It could be triangular, for example.
Triangular. Okay, that's interesting. Yeah. No, we didn't try that. Yeah.
Because I'm doing similar project and also exploring the triangular geometry.
Okay.
Then
Yeah. We had some Google quantum hardware and now the new IBM 2D layout in mind. That's why we did this 2D connectivity. Yeah, but it would be interesting to see
the triangular case.
Yeah.
I think it's worth clarifying that the square grid is the qubits, not the Ising model. The Ising.
Yes. It's still a 1D Ising model. Yeah, we believe it would be possible to do it for like a 2D Ising model and so on. Of course, it's going to be a bit more larger and so on, but you still, I assume, will be able to exploit the underlying structure. Yeah.
Thank you.
So it's the whole key point here is we exploit the structure of the model. Yeah.
You have some really nice results with like nearest neighbor, like spin models.
Yeah.
If you have long range Coulomb terms, you're going to have Dicke-states with higher order excitations. Are they also efficient to do?
Yes. Yeah.
Okay.
There is a whole literature on it, and for example, the two nearest neighbor interaction, Dicke-state, so they still have linear depth.
So okay.
Yeah, so I assume for the long range too. It's yeah, but it's something interesting to look at and see. Yeah, and of course, what I've presented here today is mainly about like a few simple models, but we believe that all these techniques generalizes to many more complicated models. But we were really interested in see like, can we get things which are beyond the Ising model? Of course, we can simulate it classically, but for example, the XYZ model, it's much harder to simulate or impossible classically, and still bringing it within reach of actual hardware. And as a last example, I also have now for time evolution. So if we combine like a Hadamard test and time evolution to measure the Loschmidt echo, then yeah, what we can do is we put the time evolution operator in here, and then we can measure the value here. Of course, what we can do is we can approximate this time evolution operator because it's an exponential by a polynomial. And we know that we have a polynomial circuit implementation for FOQCS LCU. We can control it. Also, the polynomial one we can control with, I think in this case, it's 4 extra CNOT. course, we need a bunch of extra ancilla qubits, but we are able to estimate that Loschmidt echo. And to illustrate that this is within reach, I have a plot here where we have the circuit, the CNOT depth for a polynomial, degree D polynomial in H of the 1D Heisenberg XYZ model, where we have the number of sides on the horizontal axis and the vertical axis is the degree of the polynomial. And especially since current hardware is quite noisy, we don't need to go up to extremely high polynomials. So having a rough approximation, let's say below 10 for the degree of the polynomial will already give some nice results. And what you can see is this is the CNOT depth, even for 20 sides, the degree 9 polynomial is 262, which we believe is within reach of what we will be able to do, this year or next year.
That the I in front of the H, does this, the truncation of that polynomial, I mean, it doesn't converge nicely that as
No,
yeah. So, but are there things where that is a reasonable explanation for that?
Yes, for certain models we have some.
If you've got a low magnitude H or something like that.
Yes. For certain where we try to compute the overlap with the ground state and even with the polynomial 6 or 7, we could get in the simulations up to 90%. So, and what you also could do is like using it as a initial preparation, using a low degree to get a better estimate or a better preparation of your ground state in the course of a bigger quantum algorithm. So yeah. Okay, then to conclude, I've introduced some FOQCS LCU block encodings. One of the key features is we have constant depth select oracles, only NC0 and NCZ gates, all can be performed in parallel. We need a linear number of ancilla qubits, and then by exploiting Dicke-state state preparation, we can come up with explicit and efficient block encoding circuits for 1D spin models. And this opens the door to many more practical block encodings, including controlled block encodings, polynomial transformations. And here are the two references. This we hope to submit the revision soon and hopefully get it published in Quantum. And then the second is a brand new one from last month. And then we have all the circuits on GitHub. And then to conclude, I want to just advertise a little bit CISC. So the SIAM is a Society of Industrial and Applied Mathematicians. They're one of their top journals, SIAM Journal on Scientific Computing. We have a special section open currently on quantum computing, numerical algorithms and applications, and it's quite broad. One of the two focus areas is quantum algorithms for scientific computing applications, and the second one is scientific computing methods for quantum computing science. And we will accept submissions until April the 30th, and probably that will be extended too. And with that, I would like to thank you for your attention. Sure.
Just kind of going back to Alex's question from earlier, but with the polynomial transforms on H, does the success probability depend on the polynomial degree? Yeah.
Probably, yes. Yeah. And that's also gonna drop it. Yeah,
that's it.
Because what you're changing some of the coefficients and But that's something we have to investigate further.
Yeah, well, I just asked because it's a big problem with QSVT as well, right?
Indeed. Probably we can prove that it's similar thing we have.
If the normalization coefficient is big on that.
I didn't I didn't really understand how you do the controlled PRs.
Yes, okay.
Yeah, if you,
Yeah, sure.
thank you.
It's actually this here.
Yeah.
What we have is, we know that for all the PRs we've been looking at, the first gate is an X gate. Whether it's now on the second or on the first qubit, that doesn't matter. But what we can do is we can pull that out, that X gate, and then have a PR tilde with all the remaining circuit. But if we would only use it as a general gate, we couldn't do anything. But since we use it with a particular initial state, and that's the all zero state of the ancilla qubits, we can prove that controlling the PR with all the ancilla qubits in the zero state, we don't care the top one, that corresponds to controlling this X gate, which becomes a CNOT gate, and then just PR not controlled.
So is it that if that's in a one state, that qubit, the PR basically does nothing?
That's correct.
That's what, okay.
Yes.
That bit wasn't clear to me, but I assume that if I
That's-
carefully.
Yeah. That's how we proved it. Yeah. Because if you take this X away,
Oh, yes, it's all chained
nothing
down.
happens.
Yeah, it's all chained down in the.
Could you show the circuit?
Yeah.
Sure. Let me see. Yeah.
There we are.
Hi, like for example, you have
Because it changed that.
one X gate here. If that X gate is not there, nothing happens.
Okay, that's.
And it's like here, it's on this, and we also have it, for example, here,
Yeah,
and it's everywhere.
yeah.
So actually, this method works so long as you don't actually need to be in the O0 state. You just need to start in the state with that qubit.
Yeah.
Zero.
Yeah. Yes. But it's also, if we look at the Dicke-states, it actually originates from Dicke-states.
Mm-hmm.
And to prepare a Dicke-state, you need an X gate to create, one of these
Yeah,
ones.
that's how you get the one in that one, yeah. So-
Yeah. So, and then it's all chaining down.
Mm.
And if that X is not there, then, and that's what we do. We pull that out from the Dicke-state, and then we can control that.
And if there's two excitations, is it still the same?
Yes, because the two excitations, they are prepared by a one excitation Dicke-state and then a CNOT ladder.
Okay.
And this blue block has actually also one X gate. And then as you can see why it's on the second qubit there, it's because this creates a nearest neighbor. So we start with the Dicke-state of one excitation, but n-1 qubits instead of n. And then if you have two nearest neighbor, three nearest neighbor, and so on. But this is, for example, what you would require for long-range interaction, right?
Mhm.
So it's all linear depth.
What about if you need to prepare something like D3N rather than a D2N state?
D3, okay. That's an interesting question. But I'm pretty sure it's possible to come up with an efficient circuit. Yeah.
Because like
Down to.
belongs Pauli term.
Yeah.
But yeah, I assume you make the D2N and then you have another CNOT.
Yeah.
ladder,
Yeah, probably.
Some kind.
Yeah.
I guess it gets complicated if you have different locality constraints. But anyway,
Yeah.
that's all.
Yeah. That's probably the straightforward way to do it. You go from one excitation, two excitations, three excitations. But probably if you combine it, you can do further simplifications. Because that was also in the beginning when Filippo was working on it. It was like, okay, every week he came with, I have a more efficient circuit. I further reduced the complexity factor and so on. And even like in the revision, we will have lower prefactors. So believe still further optimization is possible. Yeah, I'm still here the afternoon, so I'm happy to talk about that.
I really liked the idea that you separated the X and Z parts, and that's how like all the efficiency comes from.
Yes.
So is this idea more general? Is it more generally used in other contexts, or do you know?
That's a good question. Yeah.
They use in like error
It's
correction
used
and
for
so on.
stabilizers.
So yes.
Stabilizers
Yeah.
for stuff like that.
Yeah, and there is a paper. It was actually one of the referees who pointed that out. That there was a paper in 1997 where they also used that, but I have to check how they called it. There is, they called it symplectic notation. And it's a paper by also Shore, and it's about quantum error correction codes over GF4.
Okay.
So yeah, we were not aware of that reference, but I assume it's not that we invented it, but it was just a clever way of getting rid of the multi-controlled gates.
Yeah.
Yeah.
I have another question about the polynomial transforms. Is there some particular feature of the FOQCS block encoding that makes it possible, or could you kind of use it to generalize, say, QSVT circuits and parallelize them in general?
That's a good question. Yeah. I'm not able to answer that now. We are also looking into and also comparing, like we have now looked only near term. So CNOT depth, CNOT bounds. It might also be possible that there is an advantage if we go to T gates, because what you have in the QSVT, you have these phase factors, and that's where all these T gates are in here. We don't have in our transformations, we don't have T gates.
That was
In the select.
yeah.
We have T gates in the Pauli, and we will have T gates in the preparation oracle.
Yeah,
And they appear actually in these controlled RY gates. But we haven't done a one-to-one comparison, but we believe that it could be beneficial too. Yeah. Because what we apply is exactly the same polynomial to a matrix, what QSVT does, but without computing phase factors and so on.
Are there any restrictions on the polynomials that you can implement? Because at least the first version of QSVT has quite a few restrictions.
I don't think so, because that's related to your neighbor's question. We can always come up with a unitary, a block encoding
Yes, and
actually.
it doesn't use sufficient polynomials, so
No.
it doesn't
Yeah.
have the symmetry, because most of the symmetry constraints are from.
It's just a general polynomial, and even you could say, okay, my highest order term is 0, you can still implement it. Of course, then you're going to use too many ancilla qubits, but I think it even doesn't need to be regular, because what you do is you use a block encoding. So it might even be singular polynomials, could also be, of course, these are special cases, but I think there is no restriction on what type of polynomial.
Yeah.
But never thought about that. Like a different comparison. Yeah. Yeah, thanks for all the questions.